All right, so this is going to be the pre-lab for the percent composition and empirical formula of magnesium oxide. So this is actually a really interesting experiment. It's a little involved in the experiment end. I tried my best to show you guys as much as I could through the video. The underlying chemistry to it is fairly easy once you get it. It's trying to get a hold of it the first time that takes a little bit of practice and getting used to. So I'm just going to walk through the example problem that your lab manual has. And in that problem, it says you start with 3.497 grams of iron, you react it with oxygen, and you're left with a final mass of 5 grams. So the important thing to keep in mind is we can't create or destroy matter. So that iron we had at the beginning is also there at the end, and the mass that's different had to come from somewhere. So in this case, it would have been the oxygen. So basically what we're saying here is if I had my iron in here, so we had our iron here to start, we reacted it, and we ended up with something heavier. We ended up with an iron oxide of some sort. Now that oxygen didn't just magically appear on the iron, it came in and reacted with it because we can't create or destroy matter. So that difference in matter there, that extra whatever amount of grams that difference is going to be a result solely of the oxygen. So the way we would solve for oxygen is just that. We would take our 5.000 grams and we'd subtract from what we knew at the start, which was 3.497 grams. And when we do that, we are going to be left with 1.503 grams of oxygen. So now that we have both grams of each, we can get to the actual percent composition. Percent composition, again, is going to be similar to last week. If we think of this like a grade, it's very straightforward. So for example, if we were doing percent iron, we would say that percent iron is equal to the mass of iron divided by the mass of our product as a whole times 100. So again, with numbers, all that would be is 3.497 divided by 5 times 100. And that's going to equal 69.94%. Now, to solve for the oxygen, in this case, it's simple. We only have 2 elements here. So technically, to solve for the oxygen, we could just take 100, which would be the whole percent, subtract what the iron is, and that'll leave us with our oxygen. The other way to do this would be solving this again, just like this, but substituting the oxygen mass in there that we just solved for at the start. So if we did it that way, which is kind of the more proper way to do it, because you're not always going to have compounds that are just made of 2 elements. So if we did it the same way we did the iron, what we would have is 1.503 divided by 5 times 100, and this is going to equal 30.06%. And that's really all there is to percent compositions. Pretty straightforward. Now, empirical formulas, there's a couple extra steps to do, but it is very useful. So for those who don't remember, empirical formulas are going to give you your simplest whole number ratios between elements in a compound. So the reason I say it's actually useful for this example is we have to remember iron is one of the transition metals. And being a transition metal, iron has multiple charges. So we have both iron 2+ and iron 3+. Now, the reason why this matters is because when this combines with oxygen, it can combine in 2 ways. If it combines with the 2+ ion, we just get FeO. If it combines with the 3+ ion, we get FeO. 2O3. And again, that's just from charge balancing our compound. So iron 2 plus charge, obviously. Oxygen has a 2 minus charge, so they balance each other out. You don't need subscripts in this case. For the iron 3 plus, you need 2 of them. And for the oxygen, which is 2 minus, you need 3 of them. That charge balances it out. So you guys can see here, depending on what charge we have, is going to determine what the molar ratio between these guys is. So for the iron 2 plus, the molar ratio is just 1 to 1. For the iron 3 plus, we end up with a 2 to 3 ratio. So thankfully, empirical formulas will let us know which one we ended up forming. So the way we do that is we're going to take the masses that we had from the start and from above in the problems, because that's how we got the mass of the oxygen, and we're going to convert them to moles. Moles are going to let us relate these guys a lot better than the grams will. Remember, it's the same formula from last week. Moles are equal to grams over molecular weight. Guys, like I said last week, it's a very important formula in chemistry. If you don't walk away from this class with anything else, please remember that moles are equal to grams over molecular weight. That and probably the molarity formula is going to do you very well too, that we did last week. Will also help you for the last experiment we're going to do this year. So using that formula, we can calculate how many moles of each we have. So for iron, we had 3.497 grams. If we divide that by the molecular weight of iron, which is 55.847. And guys, for problems like this where we're dealing with things that can have rounding errors and stuff like that, try not to round until the very end. So like this is taking a lot of digits off the periodic table. Again, remember your molecular weight's always just going to be on your periodic table. It's the biggest cheat sheet you're going to have in chemistry that's given to you with every chemistry exam. So if we do this, we end up with 0.06262 moles. If we do the same thing for the oxygen, so we had 1.503. Molecular weight of oxygen is 15.9994. This is going to be 0.09394 moles. So now we're almost there. We have our moles. We just have to express this as a molar ratio. So the easiest way to do this is you find whichever one is going to be the smallest, and we're going to divide everything by that. So in this case, my moles of iron up here are my smaller one. So if I divide both sets by that, that's going to get us close to our whole number ratios. It's going to guarantee that the iron is going to simplify out to a whole number. That's because anything divided by itself is always going to equal 1. And we're going to be really close on this one. You guys will see there's going to be one extra step we got to do for the oxygen. So if we do this, again, not going to write it out because anything divided by itself will equal 1. So iron's going to equal 1. So remember, for oxygen, we had 0.09394. Trying to fix my 3 there. So we're going to divide this by the moles we had for iron, which was 0.06262. And this is going to simplify out to 1.492. So you guys can see here, we're almost there. We've got a whole number in one of them and not the other one. Remember, we need whole numbers for an empirical formula. Thankfully, if you guys look at this, if we round this up to 1.5, if we take 1.5 and multiply it by 2, that would become 3. And as long as we do it to the iron as well, it'll equal out. It's like doing the same thing to both sides of the equation. As long as you do it to both, they're going to remain equal. So I multiply each of these by 2. We're going to be left with iron being equal to 2. Oxygen will be equal to 3. And this lets us know that what we formed was actually the iron 3 compound. So we've got iron Fe2O3. So this is one of the reasons why empirical formulas are very useful. They allow us to tell the molar ratio between things at the most simplified form. And this is exactly what we're going to be doing in the experiment this week. Thankfully for you guys, if you go to page 56 in your lab manual, there's a great data sheet there that's going to help you organize all the data from the experiment video. And it's going to tell you exactly how to calculate each of these steps based off of you entering your data. So the big kind of like hint for this week is have page 56 of your lab manual open while you guys are watching the video. That way you can enter the data right to there, and you'll be able to solve everything else based off of what you enter from there. So if you guys are all set and comfortable with this, you can move on to the experimental video for this week.